So good morning all. So in the previous lecture we saw on linear mixing. Okay. So when you mix two inputs or a single input through a linear device that is an amplifier, what is your output frequency component we analyzed. Okay. So that is called linear mixing. Now it is non-linear mixing. Here also we will analyze under two conditions. A non-linear mixing with a single input and a non-linear mixing with a two inputs. So that is how our analysis will go here as well. So you could see the diagram here. You have an input V in and the corresponding frequency of your input is FA. You're giving it to a non-linear amplifier. It is a non-linear device. Okay. So a small signal amplifier is an example for linear device. However, a non-linear amplifier, example a diode, JFET, these are all examples of non-linear circuits. Okay, the output will not follow a linear relation. The output will follow a non-linear relation. So that is called non-linear device. So a simple example is diode and FET, JFET. So these are all examples of non-linear devices. So here the input-output relation is no more linear, whereas the input-output relation will be non-linear. See, if you see the expression here, V out is equal to A times VA plus B times VA square plus C times VA cube and so on. Okay, if you see this, it is a kind of infinite power series expansion. Yes or no? See, it is A into VA plus B into VA square plus C into VA cube. So plus D into VA power 4 and so on. The expression is similar to that of a infinite power series expansion. Okay, and you know that at VA, your frequency component is FA. At VA square, your frequency component is 2FA. And at VA cube, your frequency component is 3FA. Okay, so that is what. So we will understand this in depth. So before that, we will have an time domain representation and frequency domain representation. So your input is V in is equal to Vs. It is a sinusoidal signal. So it's a sine wave. Okay. Because your output is following this relation, your input-output relation in a nonlinear device is given like this: A times V in plus B times V in cube plus C times V in cube and so on. Okay. So when you draw this figure, A times VA plus B times VA square plus C times VA cube, you will get a figure like this. In time domain, if you draw, you will get a figure like this. You will have a multiple dips. Okay. And we will analyze this frequency domain after seeing this derivation. Okay. So nonlinear mixing, we are going to analyze under single input frequency. Okay. So you know that the nonlinear relationship between input and output is given by V out is equal to A times your V in plus B times V in square plus C times V in cube. Okay. So here my V in is what? VA sine 2 pi FAT, because it is a single input frequency. It is not multiple input. It is a single input frequency. So there is only one input. So V in is equal to VA sine 2 pi FAT. So what is V out? A times V in plus B times V in the whole square plus C times V in the whole cube. Okay. So A times VA sine 2 pi FAT plus B times VA sine 2 pi FAT the whole square plus C times VA sine 2 pi FAT the whole cube. Okay. So the observation is the output of a linear amplifier, the output of a non-linear amplifier with single input will have multiple components in your output. See, you're having a component at FAT the whole square plus FAT the whole cube. So you're having multiple frequency component at your output. So when you give a single input frequency component FA at your input, your output is having multiple frequency component at FAT the whole square and FAT the whole cube. Okay, so that is what. So now you could see A times V in plus B times V in square plus C times V in cube. So A times V in is nothing but linear term. Correct or not? Gain times your input. So it is a linear term or input amplified by a factor A. So this term A win is nothing but a linear term. So you have V in the whole square. So this square is nothing but a quadratic function. So a quadratic term, and this term will generate your frequency equivalent to second harmonic. See, any frequency, you can have a DC term. When you draw a sinusoidal signal, it will have a DC term, first harmonics, second harmonics, and so on. Okay. So here, what we are going to analyze is your B in square will have your frequency at 2 times FA. Okay. See, very simple. Your A into V in will have your frequency component at FA. Okay. This B into V in square. So this quadratic term, the square will come to your multiple of your FA. So that is how you will analyze your frequency component in a quadratic term. So B in square will have frequency component at 2 into FA. Okay. And V in cube will have your frequency component at 3 into FA. So this power will gets multiplied with your fundamental frequency FA. Okay. See, any signals you can have your fundamental frequency followed by its harmonics. Okay. So FA is nothing but fundamental frequency. So FA is nothing but your fundamental frequency or first harmonic, and 2FA is nothing but second harmonic, and 3FA is nothing but third harmonic. Okay. FA is nothing but your DC component or fundamental component. Okay. So in general, if I want to generalize this, so V in to the power n produces frequency n times. For example, if your frequency is F, so V in power n will have your frequency component at n into F. Okay, that is what. Okay, so V into V in square will have your frequency component at 2 into F. So my input is FA. So I will have my V in square frequency component at 2 into FA. Okay. Next one is C into V in cube. So we know that this is the relation. V in power n will produce your frequency component at n times your F, fundamental frequency. So V in square will have 2 times your fundamental frequency. V in power 3 will have 3 times your fundamental frequency. So 3 into FA. So if it is 4, you will have 4 times your fundamental frequency. Okay. So here you have your component at FA, 2FA and 3FA. Okay. So very simple. My input is what BA sine 2 pi FAT. But my output I have frequency components at fundamental frequency FA, 2FA and 3FA. That is A into VA will have frequency component at what frequency? FA. Okay. V into VA square. This 2 will get multiplied with your fundamental frequency. What is your fundamental frequency? FA. So 2 into FA. C into VA cube will have your fundamental frequency at 3 times your FA. Okay, because it is cube. Okay, whatever is your power, that power will get multiplied with your fundamental frequency. So your frequency components will be present at FA, 2FA and 3FA. Okay, at FA, what is your corresponding voltage? A times VA. So A times VA. At 2FA, what is your corresponding component? B into VA square. Okay, at 3 into FA. At 3FA, what is your frequency component? You will have a frequency component at C into VA cube. Okay, so this is how your frequency domain analysis is done. See, in our linear mixing, it is nothing but Fourier transform. When you take Fourier transform, if it is FA, VA sine 2 pi FAT, if you take Fourier transform for that, you will get a frequency component at FA because it is a linear function. But however, if you have a non-linear function like this, A into VA plus B into VA square plus C into VA cube. Okay, so your frequency component will be present at your multiples of your power. Okay, so if your power is 2, 2 into fundamental frequency, 2 into FA. Okay, if it is your power is 3, 3 into FA, fundamental frequency FA. So you will have your voltage values at your multiples of your fundamental frequency. Okay, so at your input there is only one frequency. How? See, input VA sine 2 pi FAT. So you have your component only at FA. Okay, so that is what. So that is what linear mixing with a single input. Okay, and here the important observation is new frequency components are generated. See, my input, my frequency is only at FA, but in my output I have frequency components at FA, 2FA and 3FA. Okay, so that is what new frequency components are added in my output. So my output will have different frequency components. Okay, so that is one important observation. So nonlinear amplification of a single frequency results in generation of multiples or harmonics of that frequency. Okay, so this FA, 2 times FA, 3 times FA, these multiples are called harmonics. Okay, 2FA is called first harmonic, 3FA is called second harmonic, and so on. Okay, so FA is nothing but fundamental frequency or first harmonic, 2FA is called second harmonic, and 3FA is called third harmonic, and so on. Okay, so you will have generation of harmonics as well. That is, you have your frequency components at FA, 2FA, and 3FA. That means what? Harmonics or multiples of your fundamental frequencies are also generated in your output. That is one important inference in your nonlinear mixing with a single input. And another one thing is, if your harmonics are undesired, if you do not want your harmonics, it is called, it's a kind of distortion, correct or not? If you do not want harmonics at your output, you call this function as harmonic distortion. Because nonlinear amplifier is capable of producing harmonic distortion if you do not want harmonics. But in certain applications, you want kind of harmonics. Okay, in that case, this nonlinear amplification will act as a frequency multiplication process. Why? FA, 2FA, 3FA. This is nothing but multiplying FA with 2, multiplying FA with 3. It's a kind of frequency multiplication. So when this harmonics are getting added by means of nonlinear amplification is undesired, you call it as distortion. The distortion is called harmonic distortion. Whereas in some applications, you require multiply. For example, if you want to design a frequency multiplier circuit, okay, you have learned this in your LIC, I suppose. So if you want to generate a frequency multiplier circuit, you require only this process. This harmonic should be multiplied by a factor 2, 3, and so on. So in that case, you call this nonlinear mixing process as frequency multiplication. Okay, clear? So the gist is very simple. So when you give a single input signal to a nonlinear device, so nonlinear device can be diode or JFET, you will have your output component following this input-output relation. That is A times VA plus B times VA square plus C times VA cube. So this is nothing but your input-output governing equation. Okay, and when you plot the spectrum of this, you will have your frequency component at multiples of your fundamental frequency, FA, 2FA, 3FA, and so on. Okay, this FA is called first harmonic or fundamental frequency, and 2FA is called second harmonic, and 3FA is called third harmonic. So you will have infinite number of harmonics in your output. Okay, this is an infinite power series expansion. See this CVA cube plus dot dot. So this is an infinite power series. Okay, so that is what. So linear mixing will produce harmonic distortion if your harmonics are undesired. But if you want your harmonics as desired function, it will produce frequency multiplication. So that is what nonlinear mixing with a single input. Okay. So next one is nonlinear mixing with two inputs. So far we have analyzed nonlinear mixing with a single input. Here we are analyzing it with a two input. Okay. So I'm taking this first sinusoidal figure as VA. So this is nothing but in our previous nonlinear mixing with single input, VA is nothing but VA sine 2 pi FAT, correct? Okay, but here it is two inputs, multiple inputs. So our input will be addition of these two. Okay, so we are just adding two inputs, multiple inputs. So we are just adding two inputs and giving it as an input to a nonlinear device. That is what we are going to analyze. So here we are going to analyze the added sum of two signals given as an input to a nonlinear amplifier. Okay, so my V in here is VA sine 2 pi FAT plus VB sine 2 pi FBT, because it is two signals. VA is first signal amplitude, FA is first signal frequency, and VB is second signal amplitude, and FB is second signal frequency. And you know your input output relation is given by V out is equal to A times V in plus B times V in square plus C times V in cube. So here, so A into V in. V in is what? This additive sum, correct or not? So VA sine 2 pi FAT plus VB sine 2 pi FBT. For simplifying the calculations, I'm just assuming VA sine 2 pi FAT as VA dash and VB sine 2 pi FBT as VB dash. Okay, for simplification. So what will be my V in now? VA dash plus VB dash plus B times V in square. What is V in square? VA dash plus VB dash the whole square. Okay, plus C times VA dash plus VB dash the whole cube. Okay, now I'm just expanding this. So A times VA plus A times VB plus B into, A plus B the whole square, the formula is A square plus B square plus 2AB. So VA dash square plus VB dash square plus 2 times VA dash VB dash. Okay, that is your B plus C into A plus B the whole cube. So the formula is what? A plus B the whole cube, A cube plus B cube plus 3A square B plus 3AB square. So VA dash cube plus BB dash cube plus 3A BA dash square BB dash plus 3BA dash BB dash the whole square. I'm just doing my expansion of A plus B the whole square and A plus B the whole cube. So this is what. So now I'm just analyzing this expression. So if you see, V out is A time. I'm just taking A common, B common. Sorry, I'm just taking A BA dash plus B BA dash plus C BA dash the whole cube. That is, I'm just separating this function in terms of the powers. That is, in terms of BA dash itself, BB dash itself, combination of VA dash and BB dash. See, I'm just rearranging this expression of V out. You could see this is your expansion for V out. I'm just rearranging this function of V out in such a way that I'm having it in terms of VA dash, BB dash, combination of VA dash and BB dash. So this expression is arranged in such a way that I have the expression in terms of VA dash, BB dash, and combination of VA dash and BB dash. So I can write this as A VA dash plus B VA dash the whole square plus C into VA dash the whole cube. Okay. So A VA dash plus B VA dash the whole square plus C into VA dash cube. Okay. Similarly, I'm just splitting up my BB dash also. So A into BB dash plus B into BB dash square plus C into BB dash cube. So that is my second term. A into BB dash plus B into BB dash square plus C into BB dash cube. Okay. And then remaining terms, I have what? 2 into B into VA dash VB dash. That is combination of VA and VB. And similarly, I have 3 into VA dash square VB dash plus 3 into VA dash VB dash the whole square. Okay. So that is my third term. Okay. So that function is rearranged in such a way like this. So I'm just keeping this as summation as 1, 2, and 3. This summation is kept as equation 1, equation 2, and equation 3. So if you see this first summation, you have A into VA dash plus B into VA dash square plus C into VA dash cube. Okay. So VA dash is what? VA sine 2 pi FAT. So what is your frequency component for A into VA dash FA? Okay. B into VA dash the whole square. So we know that B into B power n will have n into F. So previous expression, we have explained this. So B into VA dash square will have your frequency component multiplied by 2 into your fundamental. Okay, so what is your fundamental of VA dash? FA is your fundamental frequency. So 2 into FA is your new frequency plus C into VA cube. So VA cube means what is your fundamental for VA cube? So VA dash is nothing but VA sine 2 pi FAT. So it is multiplied by 3. So your new frequency will be 3 into FA. So this first term will have frequency components at FA, 2FA for B VA square plus 3FA for C VA cube. Okay. And your second term A into BB dash. So BB dash will have your frequency at FB. So FB. So B into BB dash square. So square means you will have your frequency component at 2 into FB. And cube means 3 into FB. Okay. So you could see that your third expression is 2 into B into VA dash VB dash plus 3C into VA dash square VB dash plus 3C into VA dash into VB dash the whole square. Okay. So you know that for VA cube, the formula is to find your frequency component as power times your fundamental. So what is the fundamental of VA dash? FA. So power times your fundamental is 3 times FA. So only you have your output at 3FA, 3FB. Now your third equation, if you analyze, it is like, let me take this term, 2 into B into BA dash into BB dash. So this 2 into B is a constant, so we will keep it as such. And what is BA dash? BA dash, BA dash is what? BA sine 2 pi FAT, and VB dash is what? VB sine 2 pi FBT. Okay. So this VA, VB all is constant. So 2B, VA, VB is a constant, and you have sine 2 pi FAT into sine 2 pi FBT. This is of the form sine A sine B. So you know what is sine A sine B? Sine A sine B is nothing but half into cos of A minus B. So FA minus FB and minus cos A plus B. What is cos A plus B? FA plus FB. Okay. So if you see this expansion of 2B VA dash VB dash, you have your frequency component at what all frequencies? At frequency FA minus FB and FA plus FB. So only because of this reason, you have your cross products for this component at FA plus FB and FA minus FB. Similarly, for 3C VA square VB dash, if you follow the same procedure, you will have your frequencies at 2 times FA plus FB and 2 times FA minus FB. Okay, so that is what. So this FA plus FB is called cross product because you have two products. It is called cross product because of multiplication you are getting this frequency. So you are multiplying VA sine 2 pi FAT with VB sine 2 pi FBT. So because of this multiplication, you are having cross products. Okay, at what frequencies? FA plus FB and FA minus FB and 2FA plus FB and 2FA minus FB and so on. Okay, so this is called cross products. Okay, when you multiply two sinusoidal signals, you have your frequency components at FA plus R minus FD and so on. So this kind of frequency component is called cross products. So harmonics means what? FA, 2FA, 3FA. So you know multiples of your fundamental frequency is nothing but harmonics. So FA, 2FA, 3FA. So first two terms corresponds to harmonics. The last term, that is this cross product, refers to cross product. Your last third term refers to your cross products. Okay. So in case of a nonlinear mixing, an infinite number of frequency components are produced. Yes, if you see the expansion, you can see I have just written only for this term and this term. Okay, this plus ditto you have. If I expand that, I will have additional frequency component also. So in general, I have infinite number of frequency components in a nonlinear mixing with two inputs. Okay, that is what. For nonlinear case, an infinite number of harmonic frequencies are produced. Okay, and you also have cross products as well. So in case of a nonlinear mixing with two inputs, two conditions are happening. One is called your harmonic distortion, the other one is called cross product. You see this expansion, you have both harmonic distortion and cross product distortion. Okay, and this modulation is nothing but this FA plus FB, FA minus FB. So this process, that is FA plus R minus FB. So your frequency component is either increased or decreased. See, FA plus FB means it is increased, correct or not? When you add two frequency, one at 100 Hertz and other at 500 kilohertz, 501 kilohertz is your answer. 1 kilohertz plus 500 Hertz is 501 kilohertz. So you are increasing your frequency. That is called up conversion. FA minus FB means you are decreasing your frequency. That is called down conversion. So this cross product, if you require cross product in some applications, this kind of up conversion or down conversion will happen. That is, your frequency component will either be increased or frequency component will either be decreased. This process is in a way is called modulation. Okay, that is, you're increasing your frequency. So if the cross products are desired, if in any application, if you want your cross products to be present, that is a kind of modulation. This cross products will lead to modulation. Okay, and if your cross products are undesired, okay, see, if you do not want cross products, then if your cross product is undesired, it is called intermodulation distortion. Okay, because two frequency components are overlapping, so that is a kind of distortion. If your cross product is desired, you call it as modulation. The cross product is not desired. If you do not want cross product, this effect is called intermodulation distortion. Okay, see, we saw something called harmonic distortion in our non-linear mixing with a single input. Okay, see, here we saw harmonic distortion. If your harmonics is undesired, you call it as harmonic distortion. Similarly, here, if your cross product is undesired, it is called intermodulation distortion. That is, intermodulation means between two frequency components, FA and FB. So only it is called intermodulation distortion. If your cross product is desired, it is called modulation. Okay. See why this cross product is called modulation. I will explain this with a simple example. We will discuss this in detail in our next sessions. But now I will say why this cross product is called modulation. See, modulation is very simple. You know, you will have a carrier and a message signal. Okay. So message signal will be of low frequency and carrier will be of high frequency. Okay. So high frequency carrier will be changed. That is, the characteristics of your high frequency carrier will be changed in accordance with your message signal. That is called modulation. Okay. So what is my carrier frequency, high frequency? So FA is 500 kilohertz we will take, and your message, let us take it as FB. So let FB be 1 kilohertz. So 501 kilohertz. So 1 kilohertz is being modulated by a 500 kilohertz carrier. So your output will have FA plus FB and FA minus FB. Okay. So FA plus FB is what? 501 kilohertz. FA minus FB is what? 499 kilohertz. So your output frequency component, if you take, you'll have both the frequency component. So your 1 kilohertz message signal is being modulated by a 500 kilohertz carrier. So there is a kind of frequency conversion. Okay. So that is why this cross product. See, if you see the cross product, you have FA plus FB and FA minus FB. So because of this reason only, we call cross product as a kind of modulation. So this cross product will lead to modulation. We will study in detail how is this FA plus FB, FA minus FB all in types of AM. So there you will get a clear idea how this modulation can be related with cross products. Okay. So for instance, now you understand that when you have cross products, that is FA plus FB or FA minus FB, it will lead to modulation. Okay. So that is what we will discuss this very detailedly. There you will get a very clear idea. Though it is vague explanation now, the future classes you will get a very clear idea. Okay. So this cross product will occur at M into FA plus or minus NFB. Okay. See here it is what? FA plus FB, FA minus FB. So 2FA plus FB, 2FA minus FB for this term. For this term, if you solve, you will have it as FA plus or minus 2FB. For this 3C VA dash VB dash square, if you find the frequency component, you will have your frequency component at FA plus or minus 2FB. So generally, if you want to express this cross product, it is FA plus or minus FB, but M into N, where M and N are some integer. Okay. So either it can be, see, here it is FA plus FB means it is both M and N will have value as 1. Here 2FA plus FB means M value is 2 and N value is 1. For this third term it is FA plus 2FB. So it is M value is 1 and N value is 2. So generally we will write your cross product as M FA plus or minus NFB, where M and N are some integers. Okay. So this is called nonlinear mixing. So to sum it up, you have nonlinear mixing with single input and nonlinear mixing with double input. So nonlinear mixing with single input will produce multiples of your harmonics. Okay. Sorry, will produce multiples of your fundamental frequencies, or it is called harmonic distortion. Whereas in your nonlinear mixing, you will have cross product. Okay. So cross products will be generated. This cross product, if it is desired, it will lead to modulation. If it is undesired, it will lead to intermodulation distortion. Okay. So that is what we have learned as part of nonlinear mixing with single input and nonlinear mixing with two inputs. Okay. So thank you.